So, in this lecture, we'll study multiplexer, or in short form, we also call it MUX. MUX is a combinational circuit, and it consists of 2 to the power n input lines, an n selection line, and one output line. So, if we call that I have a MUX with 2 to the power n cross 1, the MUX is 2 to the power n cross 1. It means it has 2 to the power n input lines and one output line. And one of these input lines will be connected to the output line at a time. This connection is made by appropriately choosing the selection lines. For example, if we take a 4 cross 1, a 4 cross 1 MUX, then it will have two selection lines, four input lines, and one output. We have to choose this S0 and S1 to make sure that at a time only one input line is connected to the output line. For this, we design this type of truth table. For S0 and S1 equal to 0, 0, my output will be equal to input 1. When my S0, S1, the selection line is 0, 1, the output will be equal to input 2. And when your S0, S1 is 1, 0, it will be equal to IP3. And when it is equal to 1, 1, it will be equal to input 4. So this is the truth table of this 4 cross 1 MUX. Similarly, we can create truth table for the larger MUXes. How would we write the input-output relationship of this MUX? We can write it either through truth table, which is a pictorial representation, or we can write it to a algebraic expression, Boolean algebraic expression. So we can just, by observing this truth table, we can write that output is equal to S0 bar S1 bar input 1 plus S0 bar S1 input 2 S0 S1 bar input 3 plus S0 S1 input 4. So if you just put all the combinations of 0, 0, 0 and 1 in S0 and S1, you will find that it will give you the corresponding truth table. So this is the truth table of 4 cross 1 MUX, and this is the corresponding Boolean expression. Right? This gives you the relationship between inputs and output. How would we realize, how can we realize this 4 cross 1 MUX using gates? This is how we can design our 4 cross 1 MUX in the lab. Actually, we did it in our laboratory. So when our S0 and S1 is, we have S0, S1 and their corresponding inverted values. So we have to convert S0 bar S1 bar with input 1. It will give us term 1, that is S0 bar S1 bar input 1. So this is S0 bar S1 bar input 1. Similarly, the output of the second AND gate is S0 bar S1 input 2. The output of the third AND gate is, if we just check it, it would be S0 S1 bar input 3. This is S0 S1 input 4. The output of the fourth AND gate is this. So we have to sum them. We have to sum all of this. So it will be input to a 4 input NOR OR gate, and the output will give you the corresponding output of this MUX. So this is how we can design a 4 cross 1 MUX. Similarly, you can design 8 cross 1 MUX, 2 cross 1 MUX, etc. Next, the point of our discussion is how can we implement any n variable function using 2 to the power n cross 1 mux. So for this, we'll take an example. Let's say that we have a two variable function in this form, which is sum of product form. So this you can write a bar b bar plus a b bar. This is what we want to realize it using 2 to the power n. If n is the number of variable of any function, we can implement it using a 2 to the power n cross 1. So in our special case, it is 2. So 4 cross 1 mux. We want to implement a two variable function using a 2 to the power n cross 1 mux. So if we have studied a 4 cross 1 mux just in our previous slides. So our output of this mux was S0 bar S1 bar input 1 plus S0 bar S1 input 2 plus S0 S1 bar input 3 plus S0 S1 input 4. The output of this mux is this. We have just discussed this in our previous slides. But our aim is to get a function whose value is this a bar b bar plus a b bar. So how can we implement it? We have to connect our S0 with A, S1 with the input B. Correct. Next, what we are going to do, we will connect input 1 with, because we want a bar b bar, so we have to connect it with 1. We have to connect this with 0 because we don't want this function. If you closely observe this output consists of all the possible minterms if we consider the selection line as a variable. So what we are doing here, if we want to implement a n variable function using 2 to the power n cross 1 mux, we have to connect those variables with the selection lines because we have seen that output consists of all the possible combination of the selection lines. Just we have to remove some of the terms if they are unwanted here. If we don't want some of the min terms here, we have to just remove it from the output of that mux. To this end, what we do, we just remove those terms by putting values of input 1, input 2, and we have to connect these input lines with either 1 or 0. So we have to connect input 4 to 0 because we just want two min terms, 0th and 2nd, that corresponds to a bar, b bar, and a b bar. So we have to connect those selection line with the input variables, and appropriately we have to choose the inputs. Input 3 to 1, input 4 to 0. If we do that, we have to, practically if we have a MUX IC, then we have to just connect it with 1, we have to connect it with 0, we have to connect it with 1, we have to connect it 0, and we have to connect it with A and B. The output of this MUX will give you this two variable function. Similarly, we can implement any n cross 1 function using 2 to the power n cross 1 mux by connecting the selection line with the variables. Correct. Just make sure that you connect S0 with the MSB. So just MSB with the MSB and LSB with the LSB. And then we have to appropriately choose these values of IP1 and IP2 in order to retain only those minterms which are required and remove those minterms which are not required. But sometimes we can also implement an variable Boolean expression using lesser number of or lower order variable mux. What it means? It means some variable function can also be implemented using 2 to the power m cross 1 mux where m is less than n. Right? When it is always, when m is equal to n, you can always realize the n variable function. The n variable Boolean expression can always be realized with 2 to the power n cross 1 mux. But sometimes or some of the Boolean expression can also be implemented with lower order mux, right? Because if we can implement some function using lower order, why should we unnecessarily use higher order mux, right? That higher order mux contains more number of, it requires more number of gates, right? So if we can implement something with lesser number of gates, so we will of course for that. Let's understand it with these examples. So this is called the universal gate characteristic of your 2 cross 1 mux or mux. So we can implement any, we are implementing two variable AND gate using 2 to the power 1 cross 1 mux. You can see that here m is less than equal to less than 2. Here we are implementing our two variable AND gate using 2 cross 1 mux. How can we do that? This property is used in order to make mux a universal gate. I mean, this property eventually make our mux a universal gate. Let's see how. So we have a 2 cross 1 mux. So the output of 2 cross 1 mux would be, because I have told you when this selection line will be 0, this will be connected. When 1, this input line will be connected to output. So output will be equal to, we can write the logic expressions like this. The input output relationship will be expressed with, by using this Boolean expression. So output will be SL bar IP1 plus SL IP2. Right? When your SL is 0, this will pass. And when your SL is 1, this will be connected to output. Our aim is to implement a two variable AND gate. Correct? For this, if you just closely observe this and this output, you will see if we just connect our SL with A, IP2 with B, and IP1 with 0. Because our aim is to have this part. If we connect SL with A, IP2 with B, you will eventually see that this part will go away, right? For this, we have to connect your IP1 with 0. If we do so, we will see the output is equal to A bar dot 0 plus AB, which is equal to output is equal to AB, which is an AND gate, of course, right? So we can implement AND gate using a 2 cross 1 mux. Similarly, can we implement a OR gate using mux? OR implementation using 2 cross 1, 2 input OR gate implementation using 2 cross 1 mux. It's a very important question. How can we do that? Let's see. So our aim is to implement fa is equal to a plus b. So if you directly use this function, it will be difficult. It will, I mean, you cannot directly match it with the output of mux. So what we do, we have a little manipulation we have studied in our previous classes, that this is also same expression, right? These expressions are equivalent. If you want to check, you can make the truth table corresponding to this function as well as truth table corresponding to this function. You will see that these two functions are equivalent. So in order either we implement a plus b or a plus a complement b, it will give you the same expressions. These are the same. So the output of 2 cross 1 mux is SL bar IP1 plus SL IP2. If we connect our SL with A, IP1 with B, and IP2 with 1, you will see that output is A bar B plus A, which is equal to A plus B. This we can verify using truth table, which we have done in our previous classes. So we are not going to repeat it. So this is how we can implement an OR gate. So just try to implement, pause the video and try to implement NOT gate using our MUX. So this is quite simple because it's one input, right? One input. Inverter is always one input. So we can implement it using 2 cross 1 MUX. Because I have told you this is always possible, right? That you can implement n input function with 2 to the power n cross 1 mux. So this type of implementation is easy. We have to just appropriately choose the IP1 and IP2 as I told you, right? See, this is tricky that if you want to implement n variable function with mux of which selection line is lesser than m. But this type of implementation is quite obvious. For this you have to just connect your SL with A, IP1 with 1 and IP2 with 0 and your output will give you the inverter output, right? Or this is an inverting gate. Next, try to implement XOR. This is the next example is very interesting. Pause the video and try to implement XOR gate using 2 cross 1 gate MUX. You can use 2 ICs if required. Just pause it and do it. This is how we can implement an XOR, 2 input XOR gate using 2 cross 1 MUX. So for this, if you see the output is SL bar input 1, SL IP2. So you have to connect input 1 with A, SL with B, input 2 with A bar and SL with, it is always connected to B. In order to get this, we have to connect this with A, this with B, and we have to connect our input with A bar. Here we have to use a NOT gate, and we have told you that how can you use a MUX, how can you utilize a MUX for the OR operation, NOT operation. What we have to do, we have to connect input 1 with 1, input 2 with 0, and this with A. So this will give you A bar. This is what we have done here in order to get A bar from A. So this is how we can implement XOR using 2 cross 1 MUX. Similarly, try to implement NAND. NAND is simple. You can do that. Try it. NOR, XNOR using